Today, we're diving into one of the most incredible scientific adventures of the 18th century. It's a story about genius, pure grit, and one very special mountain in Scotland. We're talking about the Schiehallion Experiment.
I mean, think about it for a second. How on earth do you weigh the Earth? It sounds completely impossible, right? Like a riddle. But back in the 1700s, this was one of the biggest questions in physics, and a group of scientists thought they'd found a really clever way to get an answer. And here's the best part. Their solution didn't involve some futuristic death ray or digging to the center of the planet. Nope. It involved a team hauling incredibly delicate instruments up a cold, windswept mountain in the Scottish Highlands, all to measure a tiny, tiny effect using a simple pendulum.
So, where did this wild idea even come from? Well, you have to go all the way back to the man himself, the giant of physics, Isaac Newton. He was actually the first person to seriously think about how you could possibly measure the mass of our planet.
But here's the catch. Even though Newton came up with the basic theory, he was also its biggest skeptic. He ran the numbers and basically said any real mountain would have such a tiny gravitational pull that there's no way the instruments of his time could ever detect it. He essentially said, "Great idea, guys, but don't even bother trying." So let's break down the theory. It's actually pretty elegant. You've got a plumb line, a weight on a string. It hangs perfectly straight down, pointing right to the center of the Earth's gravity. But Newton's big idea was that every object with mass pulls on every other object with mass. That means a huge mountain right next to your plumb line should pull it, just a tiny bit to the side. The real challenge? Measuring that impossibly small deflection. So, fast forward a few decades after Newton. The Royal Society in London decides, you know what, let's give Newton's impossible idea a shot. But they knew that everything, and I mean everything, depended on finding the absolute perfect mountain. You couldn't just pick any old hill. This kicked off a global search for the perfect natural laboratory.
Now, there had been an earlier try. Back in 1738, a couple of French astronomers gave it a go on the massive Chimborazo volcano in Ecuador. But the conditions were just brutal, and while they thought they saw a tiny deflection, the results were kind of murky and never really gained traction. But the search eventually led them to Schiehallion in Scotland, and this mountain, well, it had some serious advantages.
So what made this one Scottish mountain so special? I mean, look at this list. It had everything they needed. It was basically alone, so no other big hills were nearby to mess with the gravity measurements. It had this really nice, regular, almost perfectly symmetrical shape, which was a lifesaver for the math they'd have to do later. And its sides were super steep, so the scientists could get their gear right up close to the mountain's center of mass. It was, for their purposes, the perfect mountain.
All right, so finding the mountain was a huge step, but actually doing the experiment, that was a whole different level of difficult. And this grueling job fell to the astronomer royal at the time, a guy named Nevil Maskelyne.
You really have to try and picture this. We're talking 1774. Maskelyne and his crew are basically living in tents and a tiny stone hut on the side of a Scottish mountain for months on end. And the weather? Well, it was Scotland. It was awful. Constant mist, driving rain, and whipping winds. This was science done the hard way, for sure.
And the process they used was just incredibly meticulous. First, they built two tiny observatories, one on the north face and one on the south. Then, from inside each one, Maskelyne used a super precise telescope called a zenith sector to measure the positions of certain stars. By comparing the star's position relative to his plumb line from the north side, and then doing it again from the south side, he could figure out the total deflection. And he didn't do it just once, he did hundreds of observations to make sure he was right.
And after all that painstaking work, in the wind and the rain, this is what he found. A total deflection of 11.6 arcseconds. To give you some perspective, a full circle has 360 degrees, each degree has 60 arc minutes, and each arc minute has 60 arc seconds. So we're talking about a ridiculously small angle. Measuring that at all was a massive achievement.
Okay, but measuring that tiny angle was only half the job. See, to figure out the Earth's density, they also had to know the density and, crucially, the exact volume of the mountain itself. This kicked off the next phase of the project, and it led to an absolutely brilliant idea from a mathematician named Charles Hutton.
So Hutton was given this mountain of data. The survey team had taken thousands of measurements from all over Schiehallion. His job was to turn that chaotic sea of numbers into one single precise figure, the volume of the entire mountain.
And his solution to this problem was a stroke of genius. To make sense of it all, Hutton came up with a totally new idea.
He started drawing lines on his map that connected all the survey points that were at the same exact height. He literally invented the contour line. This gave him a clear 2D picture of the mountain's 3D shape and, more importantly, it let him chop the mountain up into imaginary slices and calculate the volume of each one. It was a game changer.
Okay, so now they had both pieces of the puzzle. They had the pendulum's deflection, thanks to Maskelyne, and they had the mountain's volume, thanks to Hutton. All that was left was for Hutton to put it all together. He was finally ready to weigh the world.
And this was his answer. He calculated that the Earth's average density was about 4,500 kilograms per cubic meter. Now, the modern value we have today is around 5,515, so he was off by less than 20%. For a first-ever attempt using 18th century tools on the side of a rainy mountain, that is absolutely mind-blowing.
So, why was this number such a big deal? Well, here's why. Hutton already knew the density of the rock on the surface, the kind of rock Schiehallion itself was made of, and that was only about 2,500 kilograms per cubic meter. His results showed that the Earth as a whole was almost twice as dense as the stuff on its crust.
And that led to a conclusion that was just inescapable. For the planet's average density to be that high, there had to be something way, way denser deep down inside. Hutton realized that the Earth must have a huge, heavy, metallic core. Just like that, the Schiehallion experiment gave us our very first real insight into the deep structure of our own planet.
And the discoveries just kept coming. Before this, astronomers knew the relative masses of the planets, like they could say Jupiter was 300 times more massive than Earth. But they didn't know the actual mass of any of them. By getting a real number for Earth's density, Hutton gave them an anchor for the whole system. For the very first time, scientists could calculate the actual densities of the Sun, the Moon, and all the other planets.
The Schiehallion experiment wasn't just some historical curiosity. Its legacy is just immense, and it ended up shaping entire fields of science for hundreds of years.
You can see it right here on this timeline. It was the critical first step. It was followed by more precise lab experiments, like the famous Cavendish experiment a few decades later. But Schiehallion was the one that proved it could be done. And get this, in 2007, scientists reanalyzed the whole thing with modern geological data and computers, and they found that Maskelyne's original astronomical measurements were shockingly accurate. At the time, though, its most important legacy was this. It was a stunning, real-world confirmation of Newton's law of universal gravitation. By proving that a mountain could physically pull a pendulum, the experiment showed that gravity wasn't just for planets and stars. It was a truly universal force that acted between any two objects with mass. And all of this leaves us with a pretty cool final thought. The Schiehallion experiment is just this beautiful example of human ingenuity, of taking a question that seems impossible and finding a clever, elegant way to answer it through sheer dedication. And it makes you wonder, right? What are the mountains that we're trying to measure today? What profound secrets are out there, waiting to be discovered? Maybe not with some billion-dollar super collider, but with the right idea and the grit to see it through.